Okay, limiting reagent calculations. So now we're going to approach limiting reagent problems quantitatively. Just like before with our stoichiometry, we start with a balanced equation. So as you read 1a, construct a balanced chemical equation and list what's been given underneath the appropriate substances. So pause the video, do that, and check back. Okay, so you can see I've balanced the equation. Remember to cross charges for the aluminum chloride formula on the product side. We've been told here that 4.3 moles of aluminum is being combined with 5.1 moles of chlorine. Now, are those present in stoichiometric amounts? Because if they are, then they're essentially both limiting. They're both going to be used completely. So you could check to see if that ratio is in the same ratio as 2 to 3. And if you divide 4.3 divided by 5.1, you'll come up with 0.84. So just a quick refresher, I just did 4.3 divided by 5.1 and got 0.84. And that is certainly not the same as the ratio of 2 to 3. And so you can see that these amounts are not present in stoichiometric amounts. So if they're not present in stoichiometric amounts, then one of them must run out first. And so we've been asked to determine the limiting reactant. Limiting reactant, limiting reagent, same thing. So I'm going to suggest that you label that row that you've been given as that this is what you have. This is what's available. This is what is put into the reaction flask. And I would suggest that you then calculate what is needed. So what I mean by that, this is where you calculate the stoichiometric amounts. So let's pick one, for example, the 4.3 moles of aluminum, and I'll write that here. So I'm just copying down that because that's what was given. And I'm going to say, okay, how much chlorine, how much Cl2 do we need to react all of this 4.3 moles? So find the stoichiometric amount of chlorine needed to react the 4.3 moles. So I'm going to use the ratio of 2 to 3 to figure that out. If I'm showing my work, then I'll put it below here and show that I'm calculating the moles of Cl2 needed to completely react these 4.3 moles of aluminum. So as you know, this should be familiar. We did this in the 7.1 work, the mole ratio work. I'm going to switch colors here because I want it to be obvious when I'm using the coefficients. And so 4.3 times 3 divided by 2, 6.5 moles of Cl2 are needed. Okay, so 6.5 moles of chlorine are needed. So in other words, that is the stoichiometric amount here. 6.5 moles are needed to react all 4.3 moles. So the question becomes, do I have enough? That's the question. Do I have enough chlorine? And do you? Well, you have 5.1 moles. You need 6.5. So do you have enough? No, actually, you're short, right? You don't have enough. So if you don't have enough, then that means that Cl2 is the limiting reagent, and the aluminum is present in excess. So when the moles, the stoichiometric amount of what you need is greater than what you have, then you don't have enough. And so that substance, in this case the Cl2, is the limiting reagent, which means that the aluminum is excess. So to answer the question, we were asked to determine the limiting reactant. Well, here it is here. The Cl2 is the limiting reactant. Okay, and in order to answer part B now, we're asked to determine the amount of product formed. Well, remember, the idea is that the 5.1 moles, right here, the 5.1 moles of chlorine that we originally had, that is going to completely react. This 4.3 moles that we have to start with of aluminum, remember aluminum's excess. So that 4.3 moles is not going to fully react, but the 5.1 will. So this is as if we're solving a problem, just to simplify this, or to make it look familiar. This is now like solving a problem where you know the number of moles, so the 5.1 moles here, and you're trying to find the moles of the product. Do I know the moles of aluminum? Well, I have 4.3 moles, but that's excess, so not all of that reacts. So 5.1 moles of the chlorine is actually going to react. So if I want to figure out the moles then of the product, I'm going to use that 5.1 moles of the Cl2 and use the mole ratio of chlorine to aluminum chloride. And again, I'll use the red to indicate that I'm using the mole ratio. So 5.1 times the 2 divided by the 3 gives me 3.4 moles of the aluminum chloride. Okay, so that's how much product is actually formed. So take note that in particular we took N of the limiting reagent and we determined moles amount of the product. And we used the mole ratio to do that. Okay, so in general, that's the significant step that I'm following here. I'm taking the amount of the limiting reagent, so that 5.1 moles right up here, and using the mole ratio to determine the amount of the product. Okay, in part C now, I'm asking you to find the amount of excess reagent remaining. So I'm going to mark a little bit up here again to remember that we had 4.3 moles of the aluminum, but remember that this was excess. So because the Cl2 was limiting, this is the moles that we used to determine the product. The 4.3 moles of aluminum, it doesn't all react, and we're being asked in part C to find the amount of the excess reagent, so the amount of aluminum that's remaining. So first I'll just make the statement that aluminum is excess. Right? So we have that clearly in our head. We're focused in on the aluminum. Right. So what we have to start of the aluminum is 4.3 moles. So if we can subtract what actually reacts, then that will leave us with the remaining or leftover portion. So the question is, how much of the aluminum actually reacts? So we're trying to find the amount of aluminum that reacts, which is really the stoichiometric amount of aluminum that's required to react the 5.1 moles of chlorine. Remember, this is limiting, so it all reacts. So we'll take the 5.1 moles of the chlorine and use the mole ratio to go from chlorine to aluminum, switch or write our coefficients here, and finish up with 3.4 moles of aluminum. So this is what is actually needed, or you might say what actually reacts, right? So out of the 4.3 moles to start with, 3.4 moles are going to react. So the difference, if we're subtracting those, is 0.9 moles. And essentially, that's all we need to do to finish C. The idea here is that 0.9 moles of aluminum remain after the reaction. So when the reaction stops, there'll be none of the chlorine gas left and 0.9 moles of the aluminum. Okay, so all of number 1 was dealing with amount. So I was always dealing with moles. And to make the question a little bit more complicated, we can incorporate mass. So number 2 here, I'm asking you what mass of magnesium oxide is produced when 0.25 grams of magnesium ribbon, so there's a mass being provided here, 0.25 grams of magnesium ribbon, reacts with 0.68 grams of oxygen. So ultimately, I'm looking for the mass of the product of magnesium oxide. So we're going to approach this the same way we did number 1. The only difference is that we've been given masses of both reactants. We don't know which one runs out first. So we'll need to first convert to moles so that we can write what we have in terms of moles. And then we'll go to what we need by working out the stoichiometric amounts. And we'll be able to decide or identify the limiting reagent And then after identifying the limiting reagent, we'll take the moles of the limiting reagent, convert those to moles of the product, and then take the moles of the product and convert to the mass of the product. So this is our general outline. So the first thing we'll do is find moles. So take a moment and find moles of magnesium and moles of oxygen by converting those masses to moles using molar mass. Okay, so you'll see in the first step, I didn't have a lot of space horizontally here, so I showed mass over molar mass and generated the number of moles. Here I had a little bit more space, so I showed factor label. So of course you may have done this calculation with the factor label and spread it out, totally fine. And we end up with this many moles of magnesium and this many moles of oxygen. So now that's what we have. So this is basically where we started example 1. We were given the moles of each reagent. So in number 2, we had to first take the masses and convert to moles. Next, and this is very consistent with what we did in example 1, we need to find the stoichiometric amounts. So pick one of these. For example, generally I pick the first one, but it doesn't matter. So pick one of these moles. And yes, I kept a few extra digits beyond the sig figs. I'm not rounding, I'm not at the final answer yet. And now I'll look to figure out the stoichiometric amount of O2 that's required to react that 0.0103 moles of magnesium. So here's where we use the mole ratio step again. Again, relate amounts of substances in the equation. So 2 moles of magnesium to 1 mole of O2, and we finish with 0.005. So 0.00515 moles of O2. Okay, now the big comparison. The question is, do I have enough? Right? What we're saying is that the stoichiometric amounts, this is like 0.00515 moles of O2. So here's our stoichiometric amounts right here. If this all reacts, then this is how much O2 we need. So the question is, do we have enough? Right? Do I have enough? Do I have enough O2? So we need 0.005 moles and we have 0.02 moles. Oh, the answer this time is yes, we do have enough. So if we do have enough, we have extra, then that makes O2 excess, right? So if O2 is excess, that means the other reagent, the magnesium, must be the limiting reagent. So we come back here, right, and identify the limiting reagent. So magnesium is the limiting reagent, and so now we will take the amount of the limiting reagent that we have. So make sure you look back up right here. So magnesium's the limiting reagent. Go to what you have in terms of moles. Okay, so this is what we're focusing on. I'm not looking at what I need now. I'm going to what I have of the limiting reagent right here. Magnesium's the limiting reagent, so this is what I have. So I start with, or I'm going to find the moles of the product, starting with, so the moles of MgO, starting with the 0.0103 moles of the limiting reagent of the magnesium. So again, mole ratio step will take us from moles of magnesium to moles of magnesium oxide, and it turns out that that ratio is 2 to 2. And so we have the same number of moles of magnesium oxide as we did magnesium. And then the final step, and I have broken this up in steps so that you can see that, the final step here is to find the mass of the product, the magnesium oxide, starting with the moles of the magnesium oxide. So here's where the molar mass of magnesium oxide comes into play. In 1 mole of magnesium oxide, how many grams are there? Okay, so with the molar mass of MgO, we finish up with 0.42 grams of magnesium oxide. Why did I round to 2 sig figs? Well, I started tracking back. So where did this answer come from? It came from this molar mass, 4 sig figs, back up to this number of moles, which came from this number of moles, which came from this number of moles. This number of moles came from this calculation right here. and ultimately there were 2 sig figs in the original mass, and so that's less than the 4 I have in the molar mass, so I'm rounding to 2 sig figs in the end here. So 0.42 grams of magnesium oxide. Now, once you've identified the limiting reagent, can these 2 steps here be combined into one? Absolutely. You can find the mass of the magnesium oxide, starting off with the moles of that limiting reagent, which is the magnesium, and then set up your mole ratio and then set up your molar mass. So you'll see here that I put both conversion factors that were used in each step into this one calculation and finished with the 0.42 grams of product that we had here. So these 2 steps can be combined, and really I just wanted to show you both formats so that you can choose what you prefer. I think some students are more comfortable breaking it up in steps, and others will prefer the convenience and concise nature of this calculation. So really, this is a lot like our 7.2 work, our mass-to-mass stoichiometry questions. Really what it comes down to is being able to first identify the limiting reagent. So compare the moles that you have and stoichiometric amounts of the reagents to decide which is limiting and which is excess. Once you've identified the limiting reagent, then it's the moles that you have of the limiting reagent that determine the amount of product, which you can then use to calculate the mass of the product.